if you think, the blazing midday sun is the thing that's killing a garden during a severe heat wave, you're actually only looking at half the threat.
Right, yeah.
Because the real killer, it actually operates in pitch black.
Mhm.
So, welcome to this deep dive. Today, we are analyzing a highly specific, but honestly deceptively simple piece of source material.
It really is.
It's a personal garden journal entry, and it's titled Notes on Gardening, Part 923. And it was published on June 12, 2026, by a very observant author who just signs off as Ang.
Yeah, Ang.
And, on the surface, it's just this short account of a garden enduring a severe drought. But beneath that, it is a localized, super high-stakes study in atmospheric physics and really biological endurance.
Oh, absolutely. I mean, the author has essentially documented a closed system stress test here by tracking, which specific plants survive, which perish, and all the really subtle environmental variables around them. This journal entry gives us basically a masterclass in how living organisms negotiate with these extreme, inflexible environmental forces.
Right. And our mission today is to explore those surprising underlying mechanisms of that resilience. So we are going to uncover the invisible thermodynamics and cellular biology that, frankly, determine what thrives and what completely perishes during a heat wave.
It's life or death.
Exactly. And whether you manage acres of crops or, you are just someone trying to keep a single pothos plant alive in a dry apartment, understanding the physics of how things survive extreme stress is incredibly relevant to you.
It applies everywhere. Yeah.
So, okay, let's unpack this because the conditions Ang is dealing with are just brutal. I mean, the garden is suffering through a severe heat wave and drought season. And right away, Ang highlights this super counterintuitive threat. The water evaporation rate is extremely high, but Ang emphasizes that it is high, especially during the night.
What's fascinating here is the mechanics of vapor pressure deficit, or VPD for short.
VPD, right?
Yeah, because we intuitively associate evaporation with direct sunlight, right? Like photons physically hitting the soil and turning liquid into gas.
Sure, that's what we all picture.
Exactly. But evaporation is primarily driven by the atmosphere's capacity to hold water. So during a severe heat wave, the atmosphere becomes incredibly dry. It acts like this giant invisible sponge.
Just soaking it up.
Right. If the air is hot and dry, the VPD is high, meaning the atmosphere is literally exerting a suction force. It's pulling moisture out of the soil and, crucially, out of the leaves of the plants.
So it's actively pulling. I want to visualize this for you because it completely changes how we think about resting at night.
Mm-hmm.
Imagine you go to bed exhausted, right?
Mm-hmm.
And you put a full glass of water on your nightstand. You expect it to be there in the morning.
Naturally.
But the ambient temperature in your bedroom is so hot and the air is so completely devoid of humidity that the thermal energy in the room is physically vibrating the water molecules in that glass all night long.
Just nonstop.
Right. The molecules are vibrating so intensely that they break the surface tension and turn into vapor. By the time you wake up, the atmospheric vacuum has completely emptied the glass. You were supposed to be recovering, but your vital resources were just being quietly siphoned off in the dark.
That's a perfect way to put it, because from a biological standpoint, plants desperately need the nighttime to execute cellular repair. During the day, under severe heat, a plant basically goes into lockdown.
It just shuts off.
Pretty much. It closes its stomata, which are those microscopic pores on its leaves, to prevent the atmosphere from sucking all its internal moisture out. So photosynthesis largely stops.
Okay, so it's just surviving during the day.
Yeah, it's just holding its breath.
Yeah.
When the sun goes down, the temperature is supposed to drop, right, which lowers that vapor pressure deficit.
Mm-hmm.
The atmospheric suction eases up. Then the plant can finally open its stomata, pull water up through its xylem, and repair the damaged proteins from the day's heat.
But Ang's journal entry points out that this cool down isn't actually happening. Like the evaporation rate is staying high all night. Why doesn't the suction ease up when the sun vanishes? I mean, the sun is gone.
It's because of the thermal mass of the environment.
The thermal mass.
Yeah. The soil, the concrete pathways, the rocks in the garden, they have all been acting as thermal batteries all day long. They absorb shortwave solar radiation from the sun. So when night falls, they begin emitting that stored energy as long-wave thermal radiation.
Oh, wow.
Yeah, the physical ground is literally acting like a space heater, keeping the ambient air temperature incredibly high.
So it doesn't even matter that it's dark.
Not at all. The air stays hot, meaning its capacity to hold water stays massive. The vapor pressure deficit remains punishingly high. That atmospheric vacuum we talked about, it never shuts off.
So the plant never gets to open its pores. It never gets to pull that water up to repair itself.
It gets absolutely zero recovery time. And what happens is the plant's internal water reserves are continuously depleted through something called cuticular transpiration.
Wait, what is that?
It's where moisture just bleeds directly through the waxy skin of the leaf because the external pull from the dry air is just so strong.
Even with the pores closed.
Exactly. The stress compounds exponentially day after day.
That is, I mean, if the atmosphere is acting like a vacuum, pulling moisture out of everything 24/7, it seems biologically impossible for anything to survive without constant human intervention.
You would think so, yeah.
But, that leads us directly to the anomaly in Ang's journal, because in the middle of this relentless, invisible drain of resources, we are introduced to the blue porterweed.
Ah.
Specifically, it's the Stachytarpheta jamaicensis variety. Ang notes that this plant is enduring the drought with little to no watering. And what really stands out is that even the cuttings of this plant are thriving.
Which is incredible.
It is. And Ang speculates on why this is happening and writes, quote, "Maybe it's the potting mix," end quote. But I have to push back on that.
Oh, really? Well, this raises an important question regarding the balance of the foundational environment versus inherent genetics.
Right, because we just established the terrifying scale of the threat,
Yeah.
A relentless atmospheric vacuum, massive thermal radiation from the ground. Like, how much heavy lifting can dirt really do against the laws of thermodynamics?
It's a valid point.
Is the potting mix actually the savior here, or is this just the inherent, stubborn, unbreakable cellular biology of the blue porterweed? Are we giving the potting mix way too much credit?
Well, the inherent genetic resilience is obviously a massive factor here. Stachytarpheta jamaicensis is native to tropical and subtropical regions where it has evolved to handle extreme environmental swings.
So it's used to this kind of abuse.
Exactly. At the cellular level, plants like this engage in osmotic adjustment.
Osmotic adjustment.
Yeah. When the soil gets bone dry, the plant actively pumps solutes like sugars and organic acids into its own root cells. This actually lowers the internal water potential of the roots below even the dry soil.
Wait, why would it do that?
It creates a gradient that forcefully pulls whatever microscopic moisture is left in the earth into the plant. It's a survival mechanism. Furthermore, their leaves often have specialized epidermal features, like a much thicker, waxy cuticle, which acts as a physical shield against that cuticular transpiration we discussed earlier.
So the plant itself is basically a highly engineered survival machine. It's built to hoard water and resist the atmospheric vacuum.
It really is. It is genetically programmed for hostility. However, and this is important, dismissing Ang's intuition about the potting mix would actually be a mistake.
Really? Even with all those genetics?
Yeah. The potting mix plays a crucial role in altering the physics of the root zone. Native soil, especially if it's clay-heavy, tends to compact.
Like a brick.
Right. When it dries out, it practically turns into concrete. The micropores collapse and water simply runs off the surface rather than penetrating. But a high-quality, soilless potting mix is entirely different. It's usually engineered with materials like sphagnum peat moss or coconut coir.
Okay, but what exactly are those materials doing on a microscopic level that native soil isn't?
Well, sphagnum peat moss has this incredibly unique cellular structure. It contains large hollow cells called hyaline cells, and they basically act like microscopic reservoirs, holding up to 20 times their dry weight in water.
20 times, wow.
Yeah, and then you have coconut coir, which utilizes capillary action. It's composed of highly porous fibers that create millions of tiny pathways, drawing water deep into the mix and holding it there against the pull of gravity.
Yeah, that's fascinating.
And equally important, these materials resist decomposition, meaning they maintain macropores, which are larger pockets of actual air within the soil structure.
Okay, I see. So even if the plant is flooding its roots with sugars to pull in moisture, it still needs the potting mix to physically hold on to that moisture long enough for the roots to even access it.
Precisely. The potting mix creates a localized buffer. It prevents the root zone's moisture levels from instantly matching the extreme dryness of the ambient air. So the blue porterweed has the genetic engine to survive a drought, sure, but the potting mix acts as the specialized fuel tank that prevents the engine from running completely dry during the night.
That makes a lot of sense. So we have a genetically stubborn plant and an engineered soil buffer. But Ang actually reveals one deliberate physical intervention that fundamentally tips the scales. And here's where it gets really interesting. Ang includes a crucial caveat in the text.
The location.
Yes, the blue porterweed was placed under the, quote, right microclimate, and Ang notes specifically that this location was not under full sunlight.
And that strategic introduction of shade fundamentally alters the thermodynamics of the immediate space.
Yeah, I think a lot of people just assume weather is a blanket condition. Like, if the meteorological report says it is 100 degrees outside, it's 100 degrees everywhere.
That's the common assumption, yeah.
But it's really about radiant heat absorption. Think of it like wearing a heavy black t-shirt versus a white linen shirt while you're standing in an asphalt parking lot in July.
Good analogy.
With the black shirt, the dark fabric physically absorbs the photons from the sun. Those photons excite the molecules in the cotton, generating intense thermal energy that presses directly against your skin.
And you feel like you're baking.
Right. The weather's the same, but your localized thermodynamics are punishing. But if you put on the white linen shirt, it reflects a massive percentage of those photons away. You also create a physical boundary layer of air between the fabric and your skin. So you are technically in the exact same weather system as you were a minute ago, but your specific, localized microclimate protects your biology from overheating.
That's exactly it. And the mechanics of microclimates in a garden operate on the exact same principles of localized energy transfer. By placing the blue porterweed out of direct sunlight, Ang drastically reduced the plant's solar radiation loads.
Which is huge.
It is, because when a leaf sits in direct sunlight, its physical surface temperature can spike 10 to 15 degrees higher than the ambient air temperature around it.
10 to 15 degrees, which means the water inside the leaf is literally getting closer to its boiling point.
Yes, the internal water vaporizes rapidly. This localized spike in temperature drastically increases the vapor pressure deficit right at the surface of the leaf. So that atmospheric vacuum we discussed earlier, it becomes highly concentrated and significantly more powerful on that specific plant.
Just relentless.
But by moving the plant into the shade, Ang intercepted the shortwave radiation before it could even hit the leaves.
So the shade physically blocked the photons.
Exactly. And the leaf surface temperature drops to match or even falls slightly below the ambient air temperature. The localized vapor pressure deficit plummets.
Meaning less vacuum.
Right. The stomata don't have to lock down entirely, and the roots aren't forced to work over time. The plant still experiences the generalized heat wave, obviously, but it is shielded from the absolute worst of the localized radiation. The nuance here is critical, you know. The blue porterweed didn't survive purely on its genetic merit or its soil. It survived because the gardener recognized the invisible physics at play and intentionally altered the plant's thermodynamic reality.
Man, that's such a great point. But to prove just how dangerous the baseline physics of this heat waves truly were, we have to look at the control group in Ang's garden, right?
Yeah.
We need to look at what happens when a plant doesn't have the right genetics or the right microclimate.
The other side of the experiment.
Yeah. Ang writes, quote, "On the other hand, the basil seedlings didn't fare well in such weather."
The casualties of the environmental stress test.
Exactly. And I want to look very closely at the biology of what Ang is testing here, because we are comparing blue porterweed cuttings that are thriving to basil seedlings that died. Is that actually a biologically fair comparison? I mean, seedlings are essentially infants, while cuttings are severed pieces of adult plants. Does a seedling even possess the biological hardware to survive a heat wave, regardless of the microclimate you put it in?
Biologically speaking, it is a completely asymmetrical comparison.
Right, it's totally stacked against them.
Exactly. A seedling is relying entirely on a finite microscopic energy source. When a seed germinates, it utilizes the energy stored in its cotyledons, which are the embryonic first leaves, to push a primary radicle, or root, into the soil.
So it's basically running on reserve battery from day one.
Yeah, and at this stage, the seedling has almost zero root surface area. It cannot access moisture stored deeper in the soil profile. Furthermore, its cellular walls are incredibly thin and completely lack the thick, waxy cuticle of a mature plant.
So a seedling basically has zero defensive shielding and zero access to deep water reserves. When the atmospheric vacuum of the heat wave turns on, it simply gets instantly dehydrated.
It doesn't stand a chance. The localized vapor pressure deficit pulls the moisture out of the seedling way faster than its primary root can replace it.
Oh, wow.
The cellular proteins denature and the plant just collapses. A cutting, conversely, is a piece of mature tissue taken from a fully established plant. So it already possesses fully developed, thick-walled cells and a waxy cuticle that resists cuticular transpiration. And, more importantly, the stem of a cutting holds a massive reserve of stored carbohydrates.
But wait, a cutting doesn't have roots either. It's literally just a severed stem, so how does it absorb water?
Through an extraordinary cellular process called dedifferentiation.
Dedifferentiation. Yeah.
Yes. When the stem is cut, the plant uses those massive carbohydrate reserves to form a callus over the wound. It then takes its mature, specialized stem cells and essentially hits the reset button, reprogramming them back into unspecialized cells.
It hacks its own biology.
Pretty much. And these newly unspecialized cells then reprogram themselves again, forming adventitious roots. Because the cutting has thick skin and deep energy reserves, it can afford to hunker down, resist the atmospheric vacuum, and spend days or weeks building an entirely new root system.
Wow.
The seedling has no such luxury.
So putting basil seedlings into a heat wave with massive nighttime evaporation is essentially sending an organism with no defenses into a thermodynamic shredder.
If we connect this to the bigger picture, the biological death of the basil is really merely a data point in Ang's larger system. The failure is not the focus of the journal entry. The subsequent adaptation is the focus.
That's so true. I mean, look at the final sentence of Ang's entry. Ang doesn't spiral into frustration. They don't write that basil is a weak plant or that the whole garden is a failure. Ang simply concludes, quote, "Therefore, we'll need a different strategy and we'll grow them differently next year."
Right. The environmental stress basically tested a specific botanical hypothesis. The hypothesis failed because the seedlings lacked the cellular reserves to withstand the vapor pressure deficit. The gardener's immediate response is entirely analytical. The variables must simply be adjusted.
So what does this all mean? Like, if we synthesize the underlying science of Notes on Gardening, Part 923, what are the concrete mechanisms of resilience we are walking away with here?
Well, first, we have to recognize the invisible physics of our environment. The concept of the thermal battery and nighttime vapor pressure deficit proves that resource depletion doesn't stop just because the obvious threat, like the sun, has set.
Right.
Often the environment continues to drain vital resources when an organism is most vulnerable and attempting to recover. Second, we see that survival requires a combination of internal osmotic adjustment, genetic grit, basically, and external structural support, like the capillary action of a highly engineered potting mix.
Right. It takes both the internal drive to pull the water and the external structure to hold it.
Exactly. Third, we see the profound thermodynamic impact of microclimates. By simply intercepting radiant heat with shade, you can fundamentally alter the atmospheric suction on a living organism.
Which is such a simple but powerful change.
It is. And finally, we see the necessity of dedifferentiation. When severed from its life source, the cutting survives by reprogramming its existing resources to build an entirely new system of support. The seedling fails because it lacks the reserves to adapt.
You know, the journal entry really transforms the garden from this static collection of plants into a dynamic physical negotiation with the elements.
And that physical negotiation leaves you with a thought I'd like you to carefully consider. Ang noted that they will grow the basil differently next year, using the data from this failure. Look at the initiatives, the habits, or the projects in your own life that collapsed under pressure.
Yeah.
The things that seem to simply dry up and die. What if those failures weren't the result of a flawed idea, but rather the result of a catastrophic vapor pressure deficit? What if you placed a fragile seedling into an environment with a massive invisible drain on its resources, expecting it to perform like a mature cutting?
Wow, yeah.
Perhaps the solution isn't to abandon the planting altogether. Perhaps it is an invitation to stop forcing fragile things into the full, harsh sunlight of immediate expectation, and to finally take the time to construct the physical, protective microclimate they need to build their roots.
Changing the thermodynamics of your environment might literally be the only way to finally let your roots take hold. Thank you for joining us as we explored the hidden physics of Ang's garden, and thank you for being on this deep dive with us. Take care.